We're going to start looking at the last two gas laws that we're learning in Unit 6.4, Section 0.4. So we have Gay-Lussac's law, and it says the pressure of a gas. And so we're going to fill in the word pressure in our notes. And it varies directly, so we're going to fill in the word directly with the Kelvin temperature of the gas. Notice it's again Kelvin temperature, meaning that temperature has to be in Kelvin when the volume is kept constant. Because it's a direct variation, it means when pressure goes up, temperature goes up. When pressure goes down, temperature goes down. Okay, so let's solve. We have four variables. We have pressure 1, we have temperature 1, we have pressure 2, we have temperature 2. Let's solve for each one of these, where each one is all by itself on the left hand of the equal sign. So we're going to solve for pressure 1 first, and it equals pressure 2 over temperature 2 times temperature 1. Okay, then we're going to do temperature 1. Temperature 1 equals T2 over P2, and then pressure 1 goes into the numerator. Now we're going to do for pressure 2 equals pressure 1 over temperature 1, and times both by temperature 2. Then we're going to do temperature 2 equals temperature 1 over pressure 1 times pressure 2. Okay, so there's all of your formulas. Now let's use them in some examples. Okay, so we have two examples in the notes. So it says aerosol cans carry warnings on their labels saying not to incinerate. That means don't burn it. Or store the cans above a certain temperature. This problem will show why it's dangerous to dispose or throw away of aerosol cans in a fire. So you want to throw them in a fire to get rid of them. The gas used in aerosol cans is at a pressure of 103 kilopascals. So that's a pressure. So we're going to say pressure 1. And it's at a temperature of 25 degrees Celsius. So we're going to say that's temperature 1. If the can is thrown into the fire, what will the pressure be? We don't know what that is. That's going to be our pressure 2 when the temperature reaches 928 Celsius. This is our temperature 2. So as you can see, we have two temperatures and one pressure, and we're going to solve for the other one. The first thing we have to do is we have to throw those temperatures out of Celsius and into Kelvin. We can't use Celsius for gas laws. If you go back one slide, it says the pressure of the gas varies directly with the Kelvin temperature, not with the Celsius temperature. So we're going to change temperature 1. Temperature 1 equals, and it's degrees Celsius plus 273. So that's going to be 25 degrees Celsius, which we see right here, plus 273. And this is going to give us temperature of 298 Kelvin. Then temperature 2 is 928 degrees Celsius, so we're going to do 928 plus 273, and that gives us 1,201 Kelvin. All right, now we can put those into our formula. So our formula is pressure 2 equals pressure 1 times temperature 2 all over temperature 1. So now we're going to substitute in. Pressure 1 happens to be 103 kilopascals, so we'll put that. And then temperature 2 is that 928, which goes to 1,201 Kelvin, all divided by temperature 1, which is 298 Kelvin. The kelvins cancel out, leaving us with kilopascals, and we have 415 kilopascals with 3 significant figures. Actually, 25 degrees Celsius is 2. We could go to 2 significant figures, so I will 415 to 2 significant figures is, there we go, is 420 kilopascals. That's a great amount of pressure. 2 significant figures. That would be enough to make that can explode. Okay, so we're going to do one more. So it says the pressure in a car tire is 198 kilopascals at 27 degrees Celsius. After a long drive, the pressure is 225 kilopascals. What is the temperature of the air in the tire? Assume that the volume is constant. Okay, so first thing is we have a pressure 1, we have a temperature 1, we have a pressure 2, but we don't have a temperature 2. Temperature 1 cannot stay in Celsius, it has to go to Kelvin. So 27 plus 273 equals 300 Kelvin. Now we can put everything into our formula. Temperature 2 equals temperature 1 times pressure 2 all over pressure 1, which equals, and temperature 1 is 300 degrees Kelvin. Pressure 2 is 225 kilopascals. And pressure 1 is 198 kilopascals. We do the math for this. Kilopascals cancels out. And we have 340.909 Kelvin. We go back, we have 2 significant figures, so we're going to make this 340 Kelvin, and we have 2 significant figures, okay? So then let's go and look at what does it look like with the combined gas law. So we are going to combine Boyle's law, Charles' law, and Gay-Lussac's law all together. And it states that the ratio of the product of the pressure and the volume to the absolute temperature, and again, absolute temperature is another way of saying temperature in Kelvin. Remember, 0 degrees Kelvin is the absolute 0, so this is your absolute temperature, is equal to a constant. This allows you to do calculations for situations when only the amount of gas is constant. Okay, so let's look at our formulas. Now look at, we have pressure 1, volume 1, temperature 1, pressure 2, volume 2, temperature 2. We have 6 variables. We are going to have 6 different equations. So the first one we're going to solve for is pressure 1. Pressure 1 equals pressure 2 times volume 2 times temperature 1 all over temperature 2 times volume 1. Okay? So there's a whole bunch of stuff in there. And we're going to do volume 1 equals pressure 2, volume 2 times temperature 1 all over temperature 2, pressure 1. Okay? Temperature 1 equals temperature 2 times pressure 1, volume 1, all over pressure 2, volume 2. Then we have pressure 2 equals pressure 1, volume 1, temperature 2, over volume 2, temperature 1. Then we have volume 2. Volume 2 equals, boy, that's sloppy, volume 2 equals pressure 1, volume 1, times temperature 2, had to think about it for a while, over temperature 1 and pressure 2. Then we have temperature 2, and that's the last one. Temperature 2 equals temperature 1 times pressure 2 times volume 2 all over pressure 1 times volume 1. Okay, so we have 1, 2, 3, 4, 5, 6 different variables we can solve for. So let's put that into 2 example problems. So it says the volume of a gas-filled balloon is 30 liters, so that's a volume, at 313 Kelvin. Yay, it's already in Kelvin. Temperature 1 at 153 kilopascals, so that's pressure 1. What would the volume be at standard temperature and pressure, STP? We haven't solved for that. So in your notes, you have to write standard temperature equals 273 Kelvin, which is equal to 0 degrees Celsius, and standard pressure is equal to 1 atm. Right, so now let's go and solve for volume 2. So volume 2 equals pressure 1 times volume 1 over temperature 2 divided by temperature 1 and pressure 2. So now we're going to substitute in. The first thing we're going to put in is pressure 1, which says it's 153 kilopascals. So standard pressure is 1 atm, which actually equals, we don't want it in atms, we want it in kilopascals, but we know that. That is 101.325 kilopascals. So there is no conversion. So pressure 1 is 153 kilopascals. Volume 1 is 30 liters. And temperature 2 is standard temperature, which is 273 Kelvin, all over temperature 1, which is 313 Kelvin. I'm going to put that right under the other temperature, and pressure 2 is standard pressure, which is 101.325 kilopascals. The reason I do that is that I want to show that kilopascals cancels out, Kelvin cancels out, giving us an answer in liters. I don't have enough room at the bottom of the slide, so I'm going to put it up at the top of the slide. It's basically 153 times 30 times 273. Hit equals on your computer. Hit the divide key, put parentheses, then put 101.325 times 313, close the parentheses, and hit equals. It's going to come up, and notice that the unit we have left over is liters. It's going to come up to 39.5106 liters. We go back, we see 3 significant figures here, 3 significant figures here, 3 significant figures here. We have to have 3 significant figures. So it's roughly equal to 39.5 liters. And that is 3 significant figures, and we have solved for this. So let's go to the last one, and then we are done with lecture notes. So now we have a 5-liter air sample, has a pressure of 107 kilopascals at a temperature of -50 degrees Celsius. So this is a volume, this is a pressure, and this is a temperature, and this is volume 1, pressure 1, temperature 1. If the temperature is raised to 102 degrees Celsius, this would mean temperature 2, and the volume expands to 7 liters, that would be volume 2, what will the new pressure be? Okay, so it is pressure 2 equals pressure 1, volume 1, temperature 2, all over temperature 1 times volume 2. I'm going to go change this to red, and we're going to substitute in. We're going to go down here at the bottom of the slide. I'm going to do temperature 1 equals negative 50 plus 273. Right, that's going to be 223 Kelvin. And temperature 2 is 102. So we have 102 plus 273. That's going to come out to 375 Kelvin. Okay, so now we can substitute in. Pressure 1 is 107 kilopascals times 5 liters times 375 degrees Kelvin, all divided by 7 liters. I'm going to put the 7 liters right under the 5 liters, and 223 Kelvin. We can see that liters cancels out, Kelvin cancels out, leaving us with a unit of kilopascals, which is fabulous. That's what we want. It's 107 times 5 times 375. Hit equals, divided by parentheses, 7 times 223. Close your parentheses. The calculator is going to give us 128.523 kilopascals. We go back. 5.00 has 3 significant figures. 107 has 3 significant figures. 50.0 has 3. We need 3 in our answer. It's going to be roughly 129 kilopascals. 3 significant figures. There is one more example in the notes. You can take a picture of that in class tomorrow, and you can get to work on your homework when you get into class. See you then. Bye.